Hello Math 3 and welcome to your 2.5 Ed Puzzle. So we're actually going to start with the ready here. So go ahead, flip to the ready portion of your 2.5 and let's get started. So it says the graphs of f of x equals 10 to the power of x and g of x equals log x are shown in the same coordinate plane. Make a list of the characteristics of each function. All right, so let's go ahead and try this out. So first, let's look at 10 to the power of x. What are some characteristics of this? Well, first off, let's look at what point this goes through. What good point do we have here? We have 0, 1. So we could say goes through 0, 1. All right. Now let's think of the domain. Now the domain is the x values, right? That's your input. And if we look at this graph, this is going to keep going on forever here, and this is going to keep going on forever here. So we can plug in any x value, all right? So our domain is negative infinity to positive infinity. So we would say domain is negative infinity to positive infinity. Now let's look at the range of this function. Well, if we look at this exponential function here, we actually have an asymptote right there. All right? So we can say we have an asymptote at, and then this is y equals 0. All right? So with that asymptote in mind, we can see that our range is going to be 0 to positive infinity. And how did I know that? Well, this exponential function is just going to keep approaching this asymptote, but it's never going to pass it. All right, so our range is going to be 0 to infinity. And the reason I have an open bracket here is because it's never going to actually equal 0. All right, so those are my characteristics of my exponential function. Now let's go ahead and look at my log function, see what kind of characteristics I can come up with there. So first, let's look at what point this goes through. This guy goes through the point 1, 0. All right. Now let's look at the domain. Well, this guy actually has an asymptote going this way. All right. Do you see how, right, we talked about how the log functions approach that asymptote? So we could say we have an asymptote at, and this one goes up and down, right? This is a vertical asymptote, so that's going to be x equals 0. And that asymptote gives you a domain of 0 to infinity, right? We can't go past that 0 mark. However, if we look at our range, right, our range is going to go all the way down to negative infinity, and this is going to grow slowly, but it's going to keep growing, all right? So our range is actually negative infinity to positive infinity. All right, so let's take a look at these values that we've come up with. So the exponential function goes through 0, 1. The log function goes through 1, 0. You see how those are flip-flopped? Now, let's look at the domain of our exponential. All right, our domain was negative infinity to positive infinity. Well, our range on our log function was negative infinity to positive infinity. Right? And remember when we learned about inverses, right? The range and domain swap places. So keep that in mind. Now let's look at our range. The range of our exponential function is the domain of our log function. And then remember how for the for inverses, the x and y swap. Well, let's take a look, right? Our x's and y's swapped here. And also our x's and y's swapped in terms of our asymptote. So it's pretty much just opposite. All right? So now let's go ahead and answer some of these questions. They want us to answer if it's true or false, and if it's false, they want us to attempt to correct it. All right? So for number 3, it says, every graph in the form g of x equals log of x will contain the point 1, 0. And yes, that's going to be true. All right? And the reason for that is, and we talked about this, right? All log graphs that aren't transformed are going to go through 1, 0. And the reason for that, let's think of maybe like log base 2 of x. Okay? Well, 2 to the power of 0 gives you 1, right? 2 to the power, anything to the power of 0 gives you 1. And that is why all of the log functions go through 1, 0. For number 4, it says both graphs have vertical asymptotes. So this one's going to be false, right? Our log graph had a vertical asymptote, but our exponential graph had a horizontal asymptote. So this one is false, and you would say the exponential has a horizontal. For number 5, it says the graphs f of x and g of x have the same rate of change. So let's just look at these guys. Do they look like they're growing at the same rate? All right, if I'm looking at these guys, do they look like they are growing at the same rate? No. Do you see how this exponential function, goes really fast, right? And the log function, it grows real slowly. It grows, but it grows much, much slower. All right, so that would be false. And you could say that the exponential has a higher rate of change. The functions are inverses of each other. So let's talk about this one, right? We talked about what inverses are. You switch the x and y's, you switch the domain and range. They also need to reflect, let's see if I can draw this in, over the line y equals x. And that looks like that's reflecting over y equals x. So yes, these are inverses of each other. And it's important that you understand that exponential functions and log functions are inverses of each other. And we kind of talked about that already, but that is definitely an important takeaway. The range of f of x is the domain of g of x. Well, let's look. Is the range of f of x the domain of g of x? Yes, that's true. And then the graph of g of x will never reach 3. So let's look. So let's look. G of x, we don't see it reaching 3 on this graph, all right? But when will this reach 3? Okay, so essentially we're looking for, does log of x ever equal 3? Okay, and that actually is going to reach 3 eventually, right? If we rewrite this as an exponential, we get 10 to the third, right? Well, what's 10 to the third? That's 1,000. So it will reach 3 at the point 1,000, 3. So that's false. So it does reach 3. All right. So this, hopefully, you feel a little bit more comfortable with the relationship between an exponential function and a log function, right? And I want to point out, too, keep in mind that log of x is equal to log base 10 of x, right? So that's where that base 10 comes in, and that's why these are inverses. So, for example, if I gave you like 2 to the x equals y, well, log base 2 of x is going to give you y. All right? These are inverses of each other. These are inverses. Does that make sense? If you were to plot both of these on a graph, you would see that they are inverses of each other. All right. So now I'm going to go ahead and jump ahead to problem 21. You're going to do the rest in class, but I do want to do an example. I'm going to go through number 21 so that you guys can do 22 on your own. All right. So this one is compounded interest. So one thing real quick, let's go ahead and write out our formula here. All right. Our formula is that our amount is going to equal our principal balance, 1 plus our rate over the number of times that it is compounded, to the power of number of times it's compounded, and the length of time. All right. You guys hopefully should have seen this at some point before. And if you haven't, no big deal. All you're doing is plugging in values into this function. It looks really complicated, but it's not that bad. All right. So let's kind of go over real quick what each part is. So P, that is your starting balance. All right, that is how much you deposited into the account. The rate is the rate of interest. The N is the number of times of year it is compounded. So the N is in that function twice. All right, and the T is the length of time. All right, so all we need to do is go through and figure out, you know, these different parts within the word problem. So it says, how much money will there be in an account at the end of 10 years if $3,000 is deposited at 6%? All right, so let's go ahead first. Let's do problem A. So first, they want it to be compounded annually. So if something happens annually, that means that it happens once a year. All right, so that means that our N is going to be equal to 1. All right, now let's look at our problem. We figured out what our N is. Now we got to figure out what our P, our R, and our T is. So our P is our starting amount. So that's going to be 3,000. Our rate here is 6%. Now, one thing you need to pay attention to is your percent needs to be written as a decimal. Now, if you want to write a percent as a decimal, there's two ways you can do it. One way is dividing by 100. That gives you the answer. Or you could just take your 6% and move the decimal twice. Both methods will give you this answer. If the moving the decimal gets confusing, just remember you take your percentage and divide by 100. So here our rate is 0.06. All right. Now our time they give us is 10. So now we're going to go ahead and plug this into our formula. So our principal is 3,000, or our starting amount. We've got 1 plus our rate, which is 0.06. Our N is 1 because it's compounded annually, which is once per year. So we're going to put our N in as 1 again, and our time is 10. All right. So you want to make sure that you plug this into your calculator. If you need to do it in parts to make sure that you're plugging it in properly, make sure you do that. I want you to go ahead and plug this into your calculator and see what you get. All right. So when I plugged this into my calculator, I got $5,372.54. So that would be my answer. So let's go ahead and try B. All right. So B is semi-annually. Oops. And semi-annually means 2 times per year. All right. So that means that it's going to be compounded 2 times per year. So our N equals 2. All right. And nothing else has changed. Our starting amount's the same. Our length of time is the same. And our rate is the same. So we can just steal that from this problem here. Copy and paste. The only thing that has changed when we say semi-annually is how often it is compounded. So now we're going to go ahead and plug this in. We've got 3,000 times 1 plus 0.06 over 2, right? Because our N value is now 2. And then we got to put our N value up top, so we get another 2 times 10. All right, so go ahead, plug this into your calculator and see what you get. So when I plug this in, I got $5,418.33. So next problem. We have to do this when it's quarterly. So quarterly, right, quarter, I'm going to actually copy paste this down here too. Let's see, will it work? Cool. So quarterly means that it happens 4 times, right? Quarter means 4. So that means that our n is going to be 4. And again, ooh, whoa, didn't want that. What is going on? Here we go. Copy, paste. Nothing else has changed. When we make it quarterly, the only thing that has changed is the number of times it's compounded, which is going to be 4. So now we're going to plug that in. Our starting balance is still 3,000. 1 plus our rate, which is 0.06, all over the number of times it's compounded, which is 4. Then we're going to do number of times it's compounded times the length of time. All right, so go ahead and plug this in. One thing, when you're plugging this in, make sure that these guys here stay in the parentheses. All right, you know what? Actually, I'll go ahead and show you guys how to plug this in to your calculator. So let me go ahead. If you go to your calculator, skip anyways, there we go. When you plug this in, this is what you're going to want to do. 3,000 times, and you'll do parentheses, 1 plus, and then you can go to math and get your fraction. Ooh, actually, that looks kind of gross. Let's just do this. We'll do 1 plus, and then you're going to do parentheses, 0.06 divided by 4, close parentheses. And then we need to close parentheses again. We're going to do to the power of 4 times 10. All right, so make sure you plug this into your calculator. It should look just like what I just did. So plug it in and see what you get. So when I plugged it in, I got 5,442.06. And that would be my answer there. All right, so let's go ahead and try the last one. Now, if we look at the problem for this, this is compounded daily, which they tell you right away, daily. How many times do you have a day in a year? That's 365. So they tell you that your n is 365. We know that sometimes we got a leap year, we got an extra day, but we're just going to say a normal year. All right. And again, your principal amount stayed the same, your rate stayed the same, and your time stayed the same. So we could go ahead and just, we're going to paste that in there. Awesome. All right. And I will go ahead and copy down the formula we're plugging into. So we get A equals P times 1 plus rate over the number of times compounded times number of times compounded, or to the power of number of times compounded times time. So that's our formula. Let's plug it in. So we get 3,000 times 1 plus 0.06 all over 365 to the power of 365 times 10. So again, I'm going to help you guys plug this into your calculator. So go ahead, grab your calculator. Let's hop back to this. I'm going to clear. All right. So we get our 3,000, times, and we're going to do parentheses, 1 plus, parentheses again, 0.06 divided by 365, close parentheses. I'm going to close parentheses again. To the power of, open parentheses, 365 times 10, close parentheses. So get this into your calculator. Make sure you plugged it in right. And when I calculate this, I get 5,466.09 when you round. All right, so let's go put that down. So your answer here should be 5,466.09. All right, so one thing I want to point out, when you do number 22, you're going to have a new time, you're going to have a new starting amount, and you're going to have a new rate. And remember, you're going to take your rate, ooh, whoops, that should be a 5, and divide by 100 to get it into decimal form. So make sure you do that